In this video, I'm going to be going over a new category I'm going to be adding to the channel soon that I haven't really touched on or done. But that is, I'm going to be reviewing some newer, cheaper test equipment, and one of them is going to be starting with is the handheld portable oscilloscope meters and stuff like that, and maybe other stuff down the line depending on how it goes and so forth. But I'm not going to be one of those reviewers, though, that's going to be like an advertiser. And what I mean by that is you get a lot of people that get these meters and stuff like that, and they get them for free, and they just go ahead and say, oh, yeah, this is good. It's nice and shiny. They show some signals, but they don't even do it properly. And as an engineer, it kind of pained me. I was watching some people reviewing them, and they were having a BNC to alligator clips to actually do a square wave and stuff. It was pretty funny. Or they were using a 1x probe, and you got the switchable 1 to 10x probe, and they had it switched into the 1x mode, and wondering why the bandwidth couldn't go as high, making even the meter look bad. And then they were still saying, oh yeah, this meter is good, it performs well, but yet clearly, as you're watching the video, it's performing very poorly, not even triggering properly, and having jitter and everything else like that. I was kind of like, no. And then you had the guys, for example, okay, now they're using a coax cable and stuff like that, but they're not using proper termination. So it's not, the impedance is mismatched and stuff like that. And then you had the guys, for example, that were using cheap function generators and stuff like that can't even do their proper bandwidth, so they're using it to test the bandwidth of a oscilloscope meter. And let me tell you, when we do calibrations on oscilloscopes, we actually use what you call a level RF signal generator, one that's typically a few times higher than the bandwidth that's actually on the oscilloscope that you're actually calibrating. Now, what a level function generator is pretty much it has AGC and ALC that actually levels the output, so it's nice and leveled straight across like that line right there. And at certain frequencies, you're not getting a dip and then it goes back up, like I seen on some of the reviewers' channels and stuff where they're reviewing these things, and at 5 megahertz it goes up in voltage, at 4 megahertz it goes down, and at 10 megahertz it goes back up. No, you want it to be level, so when it's level you get a straight line, especially when you're sweeping, which I'll go ahead and show you right now. But you also want to make sure too that you're actually using a function generator, arbitrary waveform generator, at minimum if you don't have a level generator that actually can meet its rated bandwidth. So let's say you're just doing it for an application use, you don't got the money to spend on a signal generator and stuff like that. You just want to show, what you can use the meter for and stuff like that. You want to get one, let's say this is 100 megahertz at 1 gigasample. You want one where the ADC is 10 times what the bandwidth of the instrument is and stuff like that. So you don't get any jitter, you don't get any anti-lacing, that type of stuff. Because otherwise, when you're measuring the full bandwidth for this thing, let's say you're using a 20 megahertz function generator, and the thing can only put out, not even like 5 times what that bandwidth is and stuff like that. It's going to introduce errors into your measurement and stuff, and that's what you don't want to do. Now, as far as doing performance checking and stuff like that, really what you want is a level signal generator. Like I said, keep the signal nice and flat like that line right there. And so when you're testing, and let me go ahead and show you, we'll go and do a sweep, and we'll slow down the sweep to 50 seconds. And we're going to sweep from 1 kilohertz to 70 megahertz, which is the full bandwidth and stuff like that. I can actually see where it starts to roll off at. So let it go down. You can see now it's rolling off. And then you can see where it starts to hit the negative 3 dP point, which is right at 70 megahertz. This instrument actually does its rated specs, at least as far as the front end goes. Now, to be honest with you, for a repetitive signal, as you can see, it's fine. It's nice and stable, even up to 70 megahertz. And there's no jitter or any artifacting or anything like that. No problem and stuff like that. And I even got to very fast waveform update on this thing. That's why I love this actual handheld oscilloscope meter. It's one of my personal favorites. Now, the thing I don't like about is the fact that the horizontal, you had to hit this button and then be able to switch the button from the vertical. Horizontal shares these same buttons here, and you got to hit this to get into it. Where on a more professional one, you can see it's all separate. Your voltage, your horizontal, your vertical sensitivity, all that's separate. You know what I mean? So here you go. And you can see as it's doing its sweep there, it's relatively flat. It's not changing much as far as the voltage, what it's measuring. And you can see there, it's nice and stable. Now, of course, you're going to get voltage drop. I'm feeding 1 volt peak to peak, but you're never going to get 1 volt peak to peak because you're going to have cable loss. And, of course, it has to go to the 50 ohm termination, which is another thing, too. You want to properly terminate it so that way it's impedance match and stuff when you're measuring, especially if you're doing like square waves, triangle waves at higher frequencies and stuff like that. So let's go ahead and speed up the sweep now. And we'll go ahead and do a much quicker sweep. Now we'll do 10 seconds and then we'll do the end sweep here, because you could also do the return time. All right. And you can see there, relatively nice and flat. And you can see there the sweep. Now we'll even go faster. So we'll go ahead and go 1 second, all right? I'm just giving you an example of what's going to be how, all right? And you can see there, nice. You can see where it starts to roll off, drop off, then go back up. That's what you want to see, you know what I mean? You want to see that this instrument is capable. And then here, now we're even going to go and test the waveform update, essentially. So we'll go sweep time here. We'll go 10 milliseconds. All right, that's going to be pretty fast. You're not going to be really able to make it out, but there you go. And you can see there, it's pretty nice. You know what I mean? This thing got very fast waveform updates, and that's what I love about this portable handheld oscilloscope meter. And you'll be seeing this a lot in my repair videos. I use this meter now quite a bit. The only thing I don't like, as you can see, I got it plugged in right now, is I also drain the battery very fast too. But it's still a good portable handheld oscilloscope meter. Now, as far as isolation goes, it's not truly isolated like this Tektronix, where all the individual channels on this thing's isolated, or your fluke scope meters and stuff like that. This is not an industrial meter, nor was it ever designed to be that way. It's more for someone that, yeah, you want, let's say you want to only use one channel and you want it to be isolated. I'll do that fine, so long as you don't got it plugged in, of course, to your computer, which is grounded, or, to the AC mains and stuff. Yeah, you'll be able to do an isolated measurement. But you wouldn't use this, for example, for checking a motor control switching or whatever, because you'll blow the ground plane on it. Where a truly isolated scope, the channels are individual and not sharing the same ground plane. So there's a difference there too, but we're going to be doing testing on that. We're going to be doing current measurement testings and stuff like that, where I'm going to take my electronic load and stuff like that, program current, and then we're going to go ahead and test to see that this is accurate up on the current ranges and stuff like that. We're also going to go and test resistance, voltage, that type of stuff, but typically most meters nowadays are using a chipset, and they're pretty accurate, at least as far as voltage and resistance and stuff like that goes. We're also going to be testing continuity testing, also in dial mode, whether the meter has also beeper when it's in dial mode or not, like if you come across a shorted diode or whatever. We're going to also be testing to see if it can actually, what the voltage it can go up to, if it can handle higher powered LEDs and stuff. We're going to be doing a lot of extensive testing. We're also going to be doing application use, so I might throw in footage of me actually using this meter when I'm repairing another piece of test equipment, or, even a reel-to-reel or whatever it is. I might be checking voltages on something. We're also going to use this meter, too, to do ripple and noise testing stuff, since it is an isolated scope, and just sensitivity, well, it's not going to be as sensitive as a benchtop oscilloscope, but it's still sensitive enough where we can do that on a switch mode supply and stuff. So we're going to be doing a lot of application testing. And then we're also going to go over, pretty much, what the current consumption is and stuff like that, what the standby current consumption is. And then we'll do a teardown and stuff like that. So that's one of the few things we're going to be doing. And like I said, I'm going to give an accurate review. Whether the meter's junk or not, whether I got it for free or not, or whether I even had to purchase it or not, I'm going to treat them all the same, essentially, and stuff like that. So you're going to see on the screen the results and stuff like that, and you can choose, hey, look, do I want to buy this meter or not? And I'm going to be doing the testing as properly as I can. I won't say I'm gonna be 100% like as good or stuff like that. Obviously, this isn't a lab, you know, like as far as you know, lab that's temp control and everything like that. But at least it'll give you an idea if the meter performs up to its specification or these manufacturers are lying. Because I've seen a lot of manufacturers, they'll claim, oh yeah, it has a 200 megasamples ADC on it. And it might only have 100 megasamples ADC in it, or they're oversampling it and it has a lot of jitter or whatever the case is. So we're gonna test for all that. So yeah, I'm gonna be doing way more accurate testing, at least as accurate as I can with the equipment that I have, and then we'll see how it goes pretty much. So one thing that I did forgot to mention, I did say that the front end was capable of 70 megahertz, no problem, which you saw earlier on the video, but this only has a 200 megasample ADC in it, so in reality, it's only good up to about 40 megahertz, at least as far as a non-repetitive signal goes. Now, on a repetitive signal, yeah, it can definitely do its 70 megahertz claim that it actually claims and stuff. Just on a non-repetitive signal, no. About 40 megahertz is the max you get out of it. And of course, a square wave even much lower because it's going to require much more to be able to get an accurate square wave on it. Where this one here, it says right there 100 megahertz front end, and it does 500 megasamples a second as far as the ADC goes. So therefore, on a non-repetitive signal, it'll be able to handle, you know, pretty much no problem up to the 100 megahertz as it claims. But as far as a square wave, of course, you'll probably get about 10 megahertz, and we'll go ahead and do that. So let's do 10 megahertz. And that's before harmonics and everything lost to create the square wave, of course. And you can see there, it still looks reasonably like a square wave, no problem and stuff like that. And a great, truly isolated scope. I love this thing, but either way it goes, though, that's kind of what you got to watch out for, what the actual ADC is. And you can't go by what they advertise, too, because a lot of Chinese manufacturers will lie about those specs, of course, or they'll oversample it, which means overclock the ADC and stuff like that. And it's not stable at what they actually overclocked it to. So that's one thing that I'm going to go over in the reviews and stuff and test for. And actually, if we can tear it down and even see what the ADC they're using, even get what the clock on the output on that ADC is, if we can figure out what ADC they're using, they didn't laser etch it off and stuff and get the pin out and stuff. We're actually going to test that too and test the output from the ADC to another DPO here and see if it's actually putting out that clock that it claims to be, so we can actually see if they're actually advertising the accurate specs. The other thing too we're going to do is rise time on there. We're going to use a pulse generator so we can measure the rise time of these portable handheld oscilloscopes and stuff like that. So that way you can know the transition from low to high and stuff like that. We can measure the time and stuff, and therefore you know what the performance pretty much overall and the whole entire functionality of the handheld oscilloscope that's going to be under test and stuff like that. So like I said, we're going to be doing a lot of extensive testing on these things in the near future. I figure it's only fair that we go ahead and put a square wave signal into this Owen HDS272S. Even though this is not a review of this particular handheld oscilloscope, I will do probably a separate video on it, but I don't even know if I'm going to do it because this has been out for a long time already and it's proven to be a good meter. But let's go ahead and just show you anyway. This is at 1 megahertz, alright? We'll put a 5 megahertz square wave into it and see what that looks like. Alright, you can see there it looks pretty decent. Let's go 10 megahertz, I expect. Alright, still looks like a square wave. Let's go ahead 15 megahertz, alright. And we'll keep doing this until it looks like a sine wave, alright. Let's go 20 megahertz. Alright. Let's go 25 megahertz, or just go 5 megahertz, and I put that wrong. 25, alright. And you can see there, still reading very accurately, but a lot of harmonic loss, obviously, which you would expect. 30 megahertz. See, now it's starting to transform into a sine wave. 35 megahertz. Yep, now it's looking more like a distortion of a sine wave, but it's 40. Yeah, and that looks pretty much like a sine wave. So there you go, 40 is the upper, and I mean, well, actually, it's like more like 25, but you can see there at 40, it's a sine wave pretty much. So let's just go and do the same thing on the Tektronix since I didn't go that high. I expect it's probably actually, you know something, let me go ahead and get this out. I took the terminator out by mistake. Give me a second. Alright. And we'll go over to Tektronix and kind of do the same testing. Make sure it don't time out. Okay, we'll go back to 1 megahertz, alright? And we'll turn the output on, of course. And you can see that's what it looks like at 1 megahertz, alright? We'll go 5 megahertz. Let's go back down. And you can see it looks pretty good with a little ringing, of course. We'll go 10 megahertz. Alright. We'll go 15 megahertz. Alright. We'll go 20 megahertz. Alright. 25 megahertz. Alright. 30 megahertz. Yeah, you can see a lot of harmonic loss. 35 megahertz. 40 megahertz. Okay, so it's doing higher than what the 45 megahertz, and yeah, that's where it looks more like a distorted sine wave. 50 megahertz. And yeah, it looks pretty much like a messed up sine wave. So there you go. I figure I'll go and at least do that. It's fair enough because I did it on this one, do that one, then I also do the rest of the testing on that one. But you can see there, this one handles a little bit higher.